Learning objectives. This chapter focuses on the following: knowledge-based systems, KBS architecture, knowledge base, inference engine, explanation and reasoning, self-learning, user interface, difficulties with KBS development process, knowledge acquisition, techniques, role of knowledge engineer KE, knowledge sharing and dealing with multiple experts, KA issues and limitations, knowledge update, update by KE, update by experts, self-learning, KA issues and limitations. Knowledge is in the head of experts. Experts have ocean of knowledge. Experts have a lot of tacit knowledge. They do not know all that they know and use. Tacit knowledge is hard, impossible to describe. Experts are very busy and valuable people. One expert need not know everything. Knowledge has a shelf life. Knowledge acquisition KA techniques. The techniques for acquiring, analyzing and modeling knowledge are: protocol generation techniques include many types of interviews: unstructured, semi-structured and structured. Reporting and observational techniques. Protocol analysis techniques used for transcription of interviews or text-based information to identify basic knowledge objects within a protocol, such as goals, decisions, relationships, and attributes. These fill up the gap between the use of protocol-based techniques and knowledge modeling techniques. Hierarchy generation techniques involve creation, reviewing, and modification of hierarchical knowledge. Hierarchy generation techniques such as laddering are used to build taxonomies or other hierarchical structures such as goal trees and decision networks. The ladders are of various forms like concept ladder, attribute ladder, and composition ladders. Sorting techniques used for capturing the way people compare and order concepts. It may reveal knowledge about classes, properties, and priorities. Matrix-based techniques deals with the construction and filling in a 2D matrix, grid, table, indicating, for example, between concepts and properties, attributes and values, or between problems and solutions, or between tasks and resources, etc. The internal elements of matrix are symbols, ticks, crosses, question marks, colors, numbers, and text. Limited information and constrained processing tasks. Techniques that either limits the time or information available to the expert while performing tasks. For example, a 20-question technique provides an efficient way of assessing the key information in a domain in a prioritized order. Diagram-based techniques include generation and use of concept maps, state transition networks, event diagrams, and progress maps. These are particularly important in capturing the what, how, when, who, and why of task events. Knowledge-based systems architecture. Knowledge base KV. The knowledge necessary for understanding, formulating, and for solving problems are the basic components of knowledge base. It is a warehouse of the domain-specific knowledge extracted from the human expertise via the knowledge acquisition module. To represent the knowledge production rules, if, then, frames, logic, semantic net is used. The knowledge base of expert system includes both factual and heuristic knowledge. Factual knowledge is the knowledge of task domain. The task domain is widely shared, typically found in textbooks or journals. Heuristic knowledge has the paradoxical collaborations like the less rigorous, more experiential, more judgmental knowledge of performance, rarely discussed, and is largely individualistic. It is the knowledge of good practice, good judgment, and plausible reasoning in the field. Knowledge base KB. If, then rules. Human experts usually tend to think along. Condition implies action or situation implies conclusion. Rules, if then, are predominant form of encoding knowledge in expert systems. These are of the form if A1, A2, up to AN, then B1, B2, up to BN. Each AI is a condition or situation. Each BI is an action or a conclusion. Knowledge base KB. Semantic networks. Here, knowledge is represented in terms of objects and relationships among objects. The objects are denoted as nodes of a graph. The relationship between two objects is denoted as a link between the corresponding two nodes. The most common form of semantic networks uses the links between nodes to represent is a and has relationships between objects. Is a and has relationships between objects. The example is given here. The example shows a car is a vehicle has wheels. This kind of relationship generates an inheritance hierarchy in the network. It lowers down the objects in the network, inheriting properties from the objects rising up. Knowledge base KB frames. Knowledge is segmented into highly modular pieces known as frames. Regarding record structure, frames are generalized. Knowledge consists of concepts, situations, attributes of concepts, relationship between concepts and procedures to handle relationships as well as attributes, values. Each concept may represent as a separate frame. The attributes, the relationship between concepts, and the procedures are allotted to slots in a frame. The contents of a slot may be of any data type, numbers, strings, functions, or procedures. The link among the frames provides identical inheritance as that provided by a semantic network. A frame-based representation is suited for object-oriented programming techniques. Working memory. Working memory refers to a task-specific data for a problem. The contents of the working memory changes depend on each problem situation. Every problem in a domain has some unique data associated with it. Data may consist of the set of conditions leading to the problem, its parameters. Data specific to the problem needs to be input by the user, while using means consulting the expert system. The working memory is related to user interface. The example shows how working memory is closely related to user interface of the expert system. Inference engine. Inference engine is a brain of expert system. Since it acts as an interpreter for analysis and processing the rules, it uses the control structure, rule interpreter, and provides methodology for reasoning. The responses given by the users and firing rules help in the execution of task matching antecedents. The major task of inference engine is to trace out its way through a junk of rules to arrive at a conclusion. Here, three approaches are used: forward chaining, backward chaining, and tree searches. Inference engine, forward chaining. Forward chaining is a data-driven method of deriving a particular goal from a given knowledge base and set of inference rules. The algorithm proceeds from a given situation to a desired goal, adding new assertions wherever they are found. A forward chaining system compares data in the working memory with the condition in the if paths of the rules and determines which rule to fire out. Example: forward chaining method. Given a rule base contains following rule set. Rule 1. If A and C, then F. Rule 2. If A and E, then G. Rule 3. If B, then E. Rule 4. If G, then D. Problem: prove that if A and B are true, then D is true. Solution: start with input given A, B is true, and then start at rule 1 and go forward or down till a rule fires is found. First iteration. Rule 3 fires. Conclusion: E is true. New knowledge found. No other rule fires. End of first iteration. Goal not found. New knowledge found at 2. Go for second iteration. Rule 2 fires. Conclusion: G is true. New knowledge found. Rule 4 fires. Conclusion: D is true. Goal found. Proved. Inference engine, backward chaining. Backward chaining is a goal-driven method of deriving a particular goal from a given knowledge base to a set of inference rules. The algorithm proceeds from backwards, such as desired goal to a given situation, adding new assertions wherever they are found. A backward chaining system looks for the action in the then clause of the rules that matches the specified goal. Example: backward chaining method. Given a rule base contains following rule set. Rule 1. If A and C, then F. Rule 2. If A and E, then G. Rule 3. If B, then E. Rule 4. If G, then D. Problem: prove that if A and B are true, then D is true. Solution: start with goal, that is, D is true. Go backward or up till a rule fire is found. First iteration. Rule 4 fires. New subgoal to prove G is true. Go backward. Rule 2 fires. Conclusion: A is true. A new subgoal to prove E is true. Go backward. No other rule fires. End of first iteration. New subgoal found at 3. Go for second iteration. Second iteration. Rule 3 fires. Conclusion: B is true. Second input found. Both inputs A and B are ascertained. Prove. Inference engine, tree searches. A knowledge base is represented as a branching network. They are: depth first search. Algorithm commences at the initial node. Check to see if the leftmost below initial node, call node A, is a goal node. If not, include node A on a list of subgoals outstanding. Then starts with node A and looks at the first node below it and so on. If there is no lower level node and goal node not reached, start from last node on outstanding list and follow next route of descending to the right. Breadth first search. Algorithm starts by expanding all the nodes and one level below the initial node. Expand all nodes till a solution is reached or the tree is completely expanded. Find the shortest path from initial assertion to a solution. Expert system shells. An expert system shell is a software development environment. It incubates the basic components of expert systems. A shell is associated with a prescribed method for building applications by configuring and instantiating these components. Shell components and description are given here. Shell components and description. Knowledge base. A store of factual and heuristic knowledge. To express knowledge about the application domain, Expert System tool provides one or more knowledge representation schemes. Some tools use both frames and if-then rules. In Prolog, the knowledge is represented as logical statements. Reasoning engine. Inference mechanisms for manipulating the symbolic information and knowledge in the knowledge base form a line of reasoning while arriving at a solution for the problem. The inference mechanism can arrange from simple modus ponens, backward chaining of if and then rules to case-based reasoning. Knowledge acquisition subsystem. A subsystem helps experts in building knowledge bases. Though collecting knowledge for solving problems and building the knowledge base, it is the biggest bottleneck in building expert systems. Explanation subsystem. A subsystem that explains the actions of systems. The explanation can range from how the final or intermediate solutions were arrived at, justifying the need for additional data. User interface. A means of communication with the user. The user interface is generally not a part of the expert system technology. However, the user interface can make a critical difference in the perceived utility of an expert system. Shell components and description. Explanation. Most expert systems have explanation facilities that allow the user to ask questions. Why and how it reached a particular sort of conclusion. The questions are answered by referring to the system goals, the rules being used along with the existing problem solving. Example, dialogue with an expert system designed to give advice on car problems. System, does the car start? User, no. System, does the engine turn over? User, yes. System, do you smell gas? User, yes. Recommendation, wait 5 minutes and try again. User, why? System, I use the rule if not start and engine turn over and smell gas, then recommendation is wait 5 minutes and try again. The rule gives the correct advice for a flooded car and knows the question to be asked to determine if the car is flooded, but it does not contain the knowledge of what a flooded car is and why waiting will help. Types of explanation. Rules trace reports on the progress of a consultation. Explanation of how the system reached to the given conclusion. Explanation of why the system did not give any conclusion. Explanation of why the system is asking a question. Knowledge acquisition. Knowledge acquisition is the accumulation, transfer, and transformation of problem-solving expertise and experience from experts and or documented knowledge sources to a computer program for constructing or expanding the knowledge base. It is a subsystem which extends its help to the experts to build knowledge bases. For knowledge acquisition, techniques used are protocol analysis, interviews, and observation. Explanation and reasoning. It is a subsystem that explains the system's actions. The explanation can range from how the final or intermediate solutions were arrived at justifying the need for additional data. Here, user would like to ask the basic questions why and how the server as a tutor is sharing the system's knowledge with the user. Explanation modules responses. Example: User, why module? System: Do you have running nose? User: Yes. System: I am trying to prove that you have cold. Do you have headache? User: Yes. System: Do you have sore throat? User: No. System: Then you do not have cold. Do you have fever? User: Yes. System: Now I'm looking at the possibility of measles. Do you have cough? User: Yes. System: I can infer measles using rule if symptoms are fever, cough, running nose, then patient has measles. Measles is concluded. User: How module? System: Since you have fever, running nose and cough, and there is a rule if symptoms are fever, cough, running nose, then patient has measles. So, measles is concluded for you. User interfaces. It is a mode of communication with the user. It provides facilities such as menus, graphical interfaces, etc. to enable the dialogue user-friendly. Responsibility of user interface is to convert the rules from its internal representation, which user may not understand, to the user understandable form. Dialogue module. User interface. System: Do you have a fever? User: Yes. System: Do you have bad throat? User: No. System: Do you have cough? User: Yes. System: Are you suffering from running nose? User: Yes. System: Are you suffering from headache? User: No. Role of Knowledge Engineer KE. The knowledge engineer has the responsibility of creating the right impression, positively communicating information about the project, understanding the expert's style, preparing the sessions, and so on. The animation given here shows the tasks performed by knowledge engineers at different stages of the knowledge acquisition. Advise the expert on the process of interactive knowledge elicitation. Set up and appropriately manage the interactive knowledge acquisition tools. Edit the non-encoded and coded knowledge base in collaboration with the expert. Set up and appropriately manage the knowledge encoding tools. Validate application of the knowledge base in collaboration with the expert. Train clients in effective usage of the knowledge base along with the expert by developing operational and training procedures. Conclusion. In this chapter, we have covered the following in detail. Knowledge-based systems, KBS architecture. Knowledge base. Inference engine. Explanation and reasoning. Self-learning. User interface. Difficulties with KBS development process. Knowledge acquisition. Techniques. Role of knowledge engineer KE. Knowledge sharing and dealing with multiple experts. KA issues and limitations. Knowledge update. Update by KE. Update by experts. Self-learning.